Welcome back to Forge College. I'm your host, and today we're jumping right into a brand new explainer for our module on developing client interactions with Solana programs. Specifically, we're tackling using Solana client libraries in Rust. Now, if you were hanging out with us for the previous lesson, building and sending transactions with Rust, you know we really got our hands dirty. I mean, we were down in the trenches, manually assembling every single byte. It was a lot. But today we're upgrading. We are moving from that tedious manual transaction assembly to a super efficient, production-ready architecture. We're going to make the system do the heavy lifting for us.
So here's the game plan for today's explainer. 1. The manual assembly struggle. 2. Enter Solana client libraries. 3. The AI-assisted workflow. 4. Validating your code. And finally, 5. Wrapping up.
Let's kick things off with Section 1, the manual assembly struggle, a necessary rite of passage.
Okay, think back to our last lesson. You had to manually construct and sign literally every single piece of a transaction. Honestly, it felt a bit like building a car completely from scratch just to, drive down the street to the grocery store. It works, but man, is it painful. And that's exactly the contrast we're tackling right now. The artisanal, manual way versus the streamlined library way. Before, you are handcrafting transactions using base Rust primitives. Painstakingly assembling instruction objects, building the message, creating the transaction, signing it with a local keypair, and finally shoving those raw bytes over the network using an RpcClient. Now, don't get me wrong, doing this is fantastic for your learning. It forces you to understand exactly what the Solana runtime expects under the hood. But let's be real, it is absolutely exhausting for everyday development.
Which brings us to Section 2. Enter Solana client libraries, working smarter, not harder.
Let's look at exactly why we make this switch and step into a much cleaner workflow. Basically, client libraries wrap up all those common manual patterns and drastically reduce the boilerplate that's just cluttering up your workspace. They expose these awesome higher-level helpers to construct instructions, and, this is absolutely crucial, they return structured results instead of those opaque raw strings. By abstracting away all that low-level serialization using the Solana_client and Solana_SDK crates, you can finally just focus purely on your application logic. You get the exact same on-chain effects, but with a fraction of the headache. It's a total game changer.
Moving on to Section 3, the AI-assisted workflow, the modern developer loop.
We are going to supercharge this new setup by treating an AI assistant like our very own junior developer. We'll get it to write the boilerplate for our custom invoke_myprogram function. But as you know, to get good output from AI, you absolutely need great input. You got to start with a highly specific starter prompt. Notice how exact this needs to be. You're asking for a Rust function named invoke_myprogram. You're explicitly naming the crates to use, Solana Client and Solana SDK. You detail the program ID, the required accounts, and your desire for idiomatic Rust error handling, like using the result pattern. You even tell the AI exactly what should be returned, a parsed confirmation struct. Setting these really strict parameters ensures your junior developer doesn't go completely off script.
Once you've got your prompt dialed in, you enter this 5-step cycle. Step 1, scaffold, using your AI prompt. Step 2, compile locally. Just a quick check to catch any missing imports or crate version mismatches. Step 3, test the invocation against a local validator or devnet. Step 4, parse and assert using a small integration test to check the signature, the slot, and the bytes. And Step 5, iterate. If a test fails, you just feed the error right back to the AI to refine it. Think of this as the scientific method of modern coding, right? You just loop through these 5 steps until the AI scaffolded output matches your baseline manual test perfectly.
Next up, Section 4, validating your code. Functional parity is king. Because look, as great as AI is, how do we actually know our junior developer didn't just hallucinate a beautifully formatted but completely broken transaction? Well, we have to prove it works. The ultimate question you must answer here is, does the easy code match the hard code exactly? Functional parity is your North Star. Your newly streamlined library-backed code absolutely must achieve the exact same confirmed results and on-chain state changes as your older artisanal manual code, no exceptions.
To guarantee this, we break our validation down into 3 strict categories of checks. First, structural correctness. This simply means the code compiles cleanly, the public APIs return proper result types instead of just panicking, and it follows idiomatic Rust. Second, functional equivalence.
The transaction must succeed, it has to produce the exact same state changes on the ledger, and the returned slot should logically advance. Third, robust parsing. If your program returns data, the client has to flawlessly decode that base 64 data into the expected byte sequence or typed struct. Checking all three of these boxes guarantees our new function is as robust as it is clean.
So the real crucial point in all this validation is what your function actually hands back to you. We want it to return a custom struct, something we'll call invocation result. This is a cleanly parsed, typed return value that contains the signature, the slot, and any decoded program return bytes. It entirely replaces those opaque, super hard-to-read RPC string outputs. Basically, it transforms raw network replies into actionable, typed client state that your Rust application can safely and easily use.
Now, what happens when things don't perfectly match up during your iteration loop? Well, if your automated tests fail, you can use this handy troubleshooting matrix to pinpoint the exact discrepancy. For example, if you see a different signature but the transaction actually succeeded, it's likely a different signer or a stale block hash, so just fetch a fresh recent block hash. If the program returns unexpected bytes, it's usually an issue with instruction data serialization or the order of your accounts, so confirm the byte sequence and your account meta order. And if you get a flat-out transaction error, you're probably missing a required signer or a writable flag. Just pinpoint the discrepancy, feed that context back to your AI, and iterate.
And that brings us to Section 5. Wrapping up. Reusable building blocks.
We've moved from painful manual assembly to a really sleek, AI-assisted workflow. Let's quickly summarize before we orchestrate these new tools. Here's what you should take away from this explainer today. First, client libraries remove repetitive wiring, which frees you up to actually focus on your application logic. Second, always parse your RPC outputs into typed structs, like our invocation result, to make your client state totally predictable. Third, make your iteration observable by writing automated tests that compare your new code against your old manual runs. And finally, validate your AI scaffolding deterministically against a local validator or testnet. By following these steps, you've successfully leveled up from raw byte assembly to a repeatable, highly validated engineering pipeline.
That leaves us with a really solid foundation. Next time, we're going to turn these single invocation building blocks into fully orchestrated workflows, covering retries, async submission, and failure handling in our next explainer, handling client operations and transaction flow. But before we go, I want to leave you with a thought. If AI can scaffold your basic transactions today, what incredibly complex on-chain logic are you going to be freed up to build tomorrow? Think about it. Anyway, don't forget to visit forge.college to learn more about this and a bunch of other incredible Web3 topics. This explainer was proudly made by Forge College. I'm your host. Keep building, keep iterating, and I'll catch you in the next one.